good morning all of you. So yesterday we were looking at application of the approximate method to flows with pressure gradient, and so this method is also called as the von Karman-Pohlhausen technique, which was originally conceived by von Karman, and he suggested that we can use higher order polynomials and we can substitute that into the momentum integral equation and try to find solution for flows including pressure gradient. So this is what the procedure that we did, and finally the equation that we obtained from the momentum integral after making all those substitutions for a quartic polynomial. So this is the final expression, and so this cannot be solved just like that analytically because it's a nonlinear ODE, because here u infinity is a function of x. Okay, so therefore we have to use some numerical method like the Euler method that we had seen that for shooting technique also. So we can just discretize this particular ordinary differential equation for many number of points starting from the stagnation point. So suppose we want to apply this to the flow past a circular cylinder. Okay, so for this we know the variation of the free stream velocity. So suppose your the free stream which is approaching the cylinder is u infinity v infinity, so we can express the velocity variation of the free stream velocity variation past the circular cylinder as u infinity sine x by r naught, or maybe I can use some capital R to indicate the radius. Okay, so this is the velocity profile obtained from the inviscid flow analysis, and so now we directly integrate this particular ODE by the Euler method, and so we start from the stagnation point. So that is where the I equal to 1 corresponds to I equal to 1, 2, 3, 4, 5, 6. So if you want to look at the coordinate system in terms of x, okay, so that corresponds to x equal to 0, which is nothing but the stagnation point. Okay, so we have also determined the value of lambda. Lambda is a function of x, as I told you, and lambda at x is equal to 0 comes out to be 7.052, because we have seen that u infinity of x at x is equal to 0 becomes 0. So in order for this particular ODE to be finite, we have to force h of k to be 0 at x is equal to 0, from which we arrive that the root for lambda is which is acceptable root is basically 7.052. Okay, so now we know the value of lambda, therefore we have the expression for z in terms of lambda for a given flow conditions like your v infinity, nu and r naught or capital R. So in fact if I use capital R here, let me use this here. So this is my cylinder radius. Okay, so this is fixed for the particular geometry and the flow condition. Okay, so I can calculate my z at the stagnation point based on the value of lambda, so that from there I can start integrating it. So now I can find the value of z at the second point, okay, that is I equal to 2, and once I do that, again I come back to this expression, okay, to this algebraic expression for which I can iteratively find the value of lambda corresponding to the new value of z. Okay, so like that I can keep doing this procedure multiple times. Okay, so for all values of z I have to keep finding the corresponding value of lambda, and then using that to calculate the other parameters like h. Okay, because all of them are functions of lambda. Okay, so if I keep doing this integration till I reach a particular point where I will find that the lambda comes to minus 12, okay, that indicates that the flow is separating at that particular point, and that is where I stop the integration. Okay, so with this method I can actually track how the boundary layer thickness, because this is nothing but delta 2 is what, the momentum thickness. Okay, so I can track how the momentum thickness is progressively growing with x, and from there I can calculate all the other thicknesses, because I know delta 1 by delta, I have delta 2 by delta, I can calculate my displacement thickness, I can calculate my boundary layer thickness, everything is a function of lambda. okay, and consequently I can also determine the point where the flow is separating, okay. So the exact angle where the flow detaches about 75 degrees, okay. So this is a rigorous way of doing it, but nevertheless it is a very good useful tool. Now otherwise when you do experimental studies and flow visualization, that is one thing, but if you do not have access to those experiments, theoretically you can use this technique, approximate technique, to determine at least to the extent where the flow separation takes place, okay. Or otherwise we have to do an expensive numerical simulation of the entire Navier-Stokes equation, which is too rigorous, okay. This is a less rigorous procedure, but nevertheless it is useful till the separation point. Beyond the separation point the boundary layer theory is not valid, okay. So this is what we have seen yesterday, a very useful technique which was proposed by von Karman and demonstrated by Pohlhausen. Now this is for flow. Let us extend this technique to heat transfer problem, okay. You can consider the same adverse pressure gradient or favorable pressure gradient flows. Let us introduce the approximate solution for temperature, okay. So heat transfer, now what we are going to do when we are looking at the Nusselt number correlation, the same way for the similarity solution we derived only for the stagnation region, okay. The same way we are going to focus as far as the heat transfer is concerned. Yes.
Is that a bit different than the bracket?
Yeah.
dz by dx is h of k by u infinity of x, so the bracket should be on the
right
before that, and it should be a plus sign.
Yeah, there should be a plus sign, you are right. Yeah, I think please correct this, you are right, okay. So this the delta x should be multiplying only this, and then this is z I plus 1 minus zi, so it becomes positive on the other side. Yeah. So okay, so if you are looking at heat transfer, we will focus our heat transfer problem to region which is close to the stagnation region, the same way we did the similarity solution. The Falkner-Skan solution for the case of m equal to 1 was nothing but the stagnation point solution, and that we had converted to cylindrical system, and that gives us the Nusselt number for the stagnation region for a circular cylinder. The same way with the approximate method we are going to do the heat transfer solution for the stagnation region. So for the same problem, let us assume that the free stream or the ambient temperature is T infinity, and the walls of the cylinder is maintained as at an isothermal condition where your T wall is constant. Okay, now this gives rise to the heat transfer problem. For as far as the temperature profile is concerned, okay, von Karman or Pohlhausen did not specify anything about how rigorous the profile should be. As far as the flow is concerned, you have to take a quartic polynomial, but with respect to temperature profile we can still use the third order polynomial that we were using before for Blasius solution. So let us define our theta T minus T wall by T infinity minus T wall, so that it scales between 0 and 1, 0 at the wall and 1 at the free stream. So this can also be assumed to be a function of some eta t, which is a non-dimensional coordinate corresponding to the thermal boundary layer, okay. So let us assume a cubic polynomial we have 4 coefficients to be determined, and here eta t is nothing but y by delta t, okay. So here this is not a similarity variable, as I said. As far as the approximate solution is concerned, your eta t does not denote any similarity, it is just your non-dimensional. When you substitute in terms of y and you get the profile, you will have terms like y by delta. So in order to make it compact, you denote your y by delta as a non-dimensional eta, but it does not mean that this is a similarity variable, okay. So of course also coincidentally for the similarity solution this turns out to be the similarity variable, okay, but here it does not have anything to do with similarity variable. So now we have to propose the boundary conditions to satisfy this particular temperature profile. So what are the corresponding boundary conditions? At y equal to 0, okay, this is basically eta t equal to 0, right. So what should be the value of theta? It should be 0, and at y equal to delta t corresponding to eta t equal to 1, okay, theta t should be 1, okay, and even at y equal to 0, now if you go on look at the higher order boundary condition from the energy equation again, be equal to alpha d square t by dy square. Of course we have neglected the viscous dissipation term, so near the wall we can neglect the inertial terms, so therefore we can also say that d square t by dy square is equal to 0, or d square theta by dy square is equal to 0, okay. In terms of eta also the same thing will apply, in terms of eta t the same condition applies, okay. Now we need one more boundary condition to close this problem. So what will be the fourth condition? 0. So at y equal to delta eta t, so your d theta by d eta t should be equal to 0. So now you have the required boundary conditions, you can get the profile for theta, and what will be the profile? We have already done the same thing for Blasius solution, we have assumed a cubic profile, same boundary conditions, okay. So what was the profile? 3 by 2 eta t minus 1 by 2 eta t cube, okay. So as far as the temperature is concerned, so it does not matter, you know, I mean it only depends on the flow problem. The flow problem is different for the pressure gradient and without pressure gradient, and as far as the temperature profile is concerned, so this is the temperature profile, and the energy integral equation also remains the same, okay. So you have to substitute this into the energy integral. Do you remember the energy integral equation for without the viscous dissipation term? So let me erase this part. So I hope you can recollect the energy integral d by dx, okay. So what should be the term inside? Integral 0 to delta t. Now I am going to transform the variables from y to eta. So 0 to 1, 1 minus theta u by u infinity into d eta t, okay. So this will be d eta by, so you have basically dy there, okay. So dy by d eta into d eta by dy, okay. So basically that will be delta t, that will come outside, and on the right hand side you have your alpha dt by or d theta by d eta t at eta t equal to 0, and you have also from the transformation of variables you get u infinity into delta t. Okay, so this is your energy integral expression. Let me call this as now equation. Let us call the profile as equation number 2 and the energy integral expression as number 1. Okay, so all of you are familiar with this. Okay, so you have your 1 by, so if you want me to expand again from the basic equation, so d by dx of 0 to delta t 1 minus theta u by u infinity dy. Okay, so this I am writing in terms of eta, so 0 to 1 minus theta u by u infinity into dy by d eta t into d eta t, and dy by d eta t is nothing but delta t. Okay, so that's how this factor delta t comes. Okay, so this is my left hand side, and on the right hand side I have is equal to alpha dt or d theta by dy at y equal to 0. Okay, this I can write as alpha d theta by d eta t at eta t equal to 0 into d eta t by dy. Okay, d eta t by dy is 1 by delta t, so that's why I have the factor delta t here. Okay, and there should be, so yeah, so I am multiplying and dividing by u infinity here, so that u infinity should be taken to the right hand side. Okay, this is originally 1 minus theta into u dy, so I am multiplying and dividing by u infinity, and this u infinity is going to the, so this is the final form in terms of non-dimensional theta and non-dimensional coordinate eta t. Okay, so I can now substitute my temperature profile and the velocity profile that I obtained from the quartic polynomial into this particular equation 1. So substituting for the temperature profile 2 and velocity profile from a quartic polynomial into 1. So I have d by dx. Okay, I am taking my u infinity to the left hand side. I have delta t 0 to 1 minus 3 by 2 eta t minus plus eta t cube, and my velocity profile u by u infinity will be so what will be the velocity profile u by, what was that we derived yesterday, 1 by 2, where is this coming from?
2 eta minus 2 eta cube plus eta to the power 4.
Yeah, so if you substitute everything in a compact notation, it was f of eta plus lambda g of so eta, right? So where your f of eta was what? 2 eta minus, so this was what, probably your 2 eta minus 2 eta cube plus eta power 4. Your g of eta should be 1 by 6 eta into 1 minus eta the whole cube. Okay, and your lambda is nothing but non-dimensional pressure gradient parameter, which can be written as del square by nu du infinity by dx. In terms of dp by dx, your du infinity by dx can be written as minus del square by u infinity nu into dp by dx. So for flows with adverse pressure gradient, your lambda will be negative. With favorable pressure gradient, lambda will be positive. So this was the velocity profile that we derived yesterday, assuming a quartic polynomial and satisfying those 5 boundary conditions. Okay, so your lambda here is the non-dimensional parameter, which is giving us something like a ratio of your pressure gradient to, or pressure forces to the viscous forces. Okay, so this is one measure of how adverse pressure gradient how adverse the pressure gradient you maintained is, okay, and what is the criteria for separation is given by lambda. So lambda equal to -12 indicates the point of separation. Okay, now from this we can substitute for the velocity profile. So this will be f of, we will put it in terms of f of eta plus lambda g of eta, okay, d eta t. D eta t is the variable with which you are integrating, and that is it. Okay, so this is your left hand side basically. On the right hand side this will be equal to alpha by u infinity I have taken to the left hand side, you have d theta by d eta t. So from this profile, what is d theta by d eta t at eta t equal to 0? 3 by 2, and you have already alpha by delta t. Okay, so this will be your equation. Now we can introduce my zeta as which is nothing but delta t by delta, and from the way that we have introduced y by delta as my eta, and eta t is equal to y by delta t. So this is nothing but the ratio of eta by eta t. Okay, so I am just introducing a parameter called zeta. Now if I, for a given Prandtl number, you know that this delta t by delta is a function of Prandtl number, so this becomes fixed for a given Prandtl number. And also if you have starting, if you do not have any unheated starting length, that means you maintain an isothermal temperature condition right from the beginning. Okay, so this zeta is going to be a constant, because both the thermal boundary layer and the momentum boundary layer will grow simultaneously, and for a given Prandtl number that ratio of the boundary layer thicknesses has to be a constant. So therefore this zeta will not be a function of x anymore, it will be constant if you heat the cylinder right from the beginning. Okay, so right now we are considering a case which is isothermal throughout. Okay, we do not have any unheated starting length. Okay, so in that case you can take your zeta as a constant, you can write your delta t in terms of zeta and delta, and also you can substitute for eta in terms of zeta and delta eta t. Okay, so now you can integrate this. Now since this is a function of eta t and you are integrating across eta t, so this will result, final expression will be independent of eta t, it will contain only terms with respect to zeta and finally delta. Okay, so that comes out to be zeta into delta. So I am writing, I am taking my delta t on the right hand side here, so and I can write this as zeta times delta into d by dx into u infinity into delta t, again I can write it as zeta into delta, and if I integrate this entire expression out in terms of eta t, so I will be getting a expression like this, 3 by 2 alpha, where my m, now m should be a function of what? Okay, now I am substituting here for eta whatever function I have, all this in terms of eta t and zeta. Okay, now if I integrate it over eta t, now what should be the resulting expression should be a function of only zeta. Okay, so therefore m will be coming out as 1 by 5 zeta minus 3 by 70 zeta cube plus 1 by 80 zeta power 4, and my n will be 1 by 6 okay. So it is not that difficult, it is just one step integration which I am not doing it here. You can just substitute for all this, for f of eta in terms of eta t and zeta, multiply these two and then you integrate it out. So you will get one bunch of expressions in terms of zeta, the other which is contained within the parameter lambda. Okay, so I am separating these two and writing it out. Okay, it's clear till here. Now if you consider a particular case where your Prandtl number is greater than 1, so now what kind of approximation does it mean on zeta? Okay, so your thermal boundary layer thickness is much smaller than your velocity boundary layer. Okay, so therefore this corresponds to the fact that my zeta is less than 1. So therefore all the higher order terms of zeta, like to second power and higher, will be very small and therefore can be neglected. Okay, so all these terms can be neglected, only you can retain the first power terms. Okay, with that we can considerably simplify this expression. Okay, so therefore neglect higher order terms of zeta, and also we are interested in the region which is close to the stagnation region. As I said, we want to get an expression for Nusselt number in the stagnation region. So this is for the case where my x by r is much lesser than 1. Okay, it's quite much lesser than 1. Okay, so for this case we have also derived the expression for delta square. Now you have to tell me what will be the expression for delta square here. If I make the approximation that it's close to the stagnation region. Okay, so my delta square comes from the expression of definition of lambda, if you remember. Okay, this is lambda nu divided by du infinity by dx, and for small values of x by r, my u infinity of x will be 2v infinity into x by r. Okay, so this will be lambda nu by 2v infinity r. Okay, so this I can substitute in first. So I have a delta here, so I can substitute my expression for delta from this into this expression, and also the value of lambda for stagnation point. Okay, we have already determined the value of lambda, which is what, 7.052. so we can substitute the value of lambda here as well as the delta from here. So and therefore the resulting expression will be, so let me call this as number 3. Okay, so substituting all these approximations now into 3, now you should be getting zeta d by dx. Okay, I have already substituted for delta. Okay, delta in terms of, so this is a, I know the value of lambda also, so I have substituted directly into delta, and this will be x times zeta square root of lambda into 12 plus lambda, which will be equal to 90 by Prandtl number square root of lambda. Okay, so I have substituted for delta from here, so everything will be in terms of lambda, and of course your zeta, you have neglected all the higher order terms. Okay, all these terms have been neglected, so this will be lambda here, this will be zeta square, only the zeta square term will be there. Okay, so this will be 1 by 5 zeta plus 1 by 60 into zeta into lambda. Okay, so if you take the zeta term out, so that will be zeta square here, and you substitute for delta in terms of whatever expression that we have, so everything will be reduced to this particular form. Let us call this as 4. Now for lambda equal to 7.052, this will be getting even more simplified, and you can expand this differential equation as x d zeta cube by dx plus 3 by 2 zeta cube 1.0048 by Prandtl number. Okay. So this is my final expression, the ODE in terms of zeta. Okay, so all I am substituting is for lambda. So this entire thing is a constant and it comes out, and of course this is also in terms of lambda. So now I can separate this d by dx. I can take this inside, so this will be lambda cube into, if I write this in terms of lambda cube, okay, suppose I ignore all the constants, I have zeta x zeta square. Okay, so I can write this as, okay, so zeta d by dx, I can take zeta cube, so this is 2 zeta into zeta square zeta into x, okay, plus I can write this as zeta cube into d by dx of x will be 1. Okay, so this is how I am expanding it. Now once again this term right here, zeta cube, zeta can be written as 2x d by dx of zeta cube, okay, into 1 by 3. Okay, so I have plus zeta cube. So basically I am dividing throughout by 2 by 3, and therefore I have this final expression. Okay, so just comes through a couple of steps of algebra, which is not that difficult. Okay, so therefore this is the final ODE, and you know now how to solve this. We can, this is a non-homogeneous ODE, but it's linear, so it's not a problem. We can directly get an analytical solution for this. We have to, the solution will be, one will be for a homogeneous ODE, which is nothing but the complementary function, the other including the non-homogeneous part separately, so that will be the particular integral. Okay, so we can combine both the solutions together. Okay, let us do that. Now you have to tell me what is the solution to the homogeneous part of this ODE. All of you take couple of minutes. You can assume some xi cube is equal to something like p or z something, and you can say that your xi cube solution will be xi cube complementary function plus xi cube particular integral. Okay, so this is the solution to the homogeneous part of the ODE, and you can do it and tell me what will be the homogeneous part solution. Okay, so that is basically it has to satisfy x d psi cube Cf by dx plus 3 by 2 Cf cube equal to 0. So this is the solution to the homogeneous part. Yes. So what should be the complementary function? 0. Why? Solve this by separation of variables. You have forgotten all your ODE basics. You can, if you are confused looking at this z cube, you can take this as some z or something like that, the zeta cube. So now then it becomes the standard form of ODE which you can separate by variables. Okay, x power minus 3 by 2. Okay, so some constant, so that is some constant into x power minus 3 by 2, right. So now how do you find the particular integral? So you say that this is some z complementary function plus z particular integral, okay, and you substitute that into the original equation, which is this. Okay, so from there you already know the solution for the complementary function. Okay, so then you calculate what is your particular integral solution from there. Okay, if you do that, you will get that your QPi will be a constant basically, which will be 0.6699 by PR. Okay, so all you have to do is substitute for this plus some Pi particular integral into this ODE 5, okay, and you get directly an expression for the particular integral, which will be constant. Finally, it will be just 0.66. So you please go back and revise if you forgot how to solve non-homogeneous ODE. Okay, non-homogeneous linear ordinary differential. This is the most basic, you know. So from this, therefore, your final solution will be zeta cube will be Cx power minus 3 by 2 plus 0.6699 by PR. So this is your final solution. Now, if you had a unheated starting length, then you could have substituted that at x is equal to x naught my zeta equal to 0. But in your case, for the present case, we'll assume that it is heated right from the beginning. Therefore, at x is equal to 0, zeta equal to 0. Okay, therefore, this constant has to be 0. Okay, so in our case, directly the solution will be 0.6699 by PR. Okay, or this will be 0.875 by PR to the power 1/3. So once you found out zeta, now the entire problem is almost nearly solved, because to get the heat transfer coefficient H is minus k dt by dy at y equal to 0 by T wall minus T infinity. Okay. Now for this particular temperature profile, can you tell me how this will reduce? I know my temperature profile for theta, which is nothing but 3 by 2 eta t minus 1 by 2 eta t cube. So this can be written as minus k. In terms of theta, this will be defined as T minus T wall by T infinity minus T wall. Okay, so dt by dy will be d theta by dy into T infinity minus T wall. Okay, so minus of that will be T wall minus T infinity. So this will be k into d theta by dy. So once again I can transform the variable as d theta by d eta t at eta t equal to 0 into d eta t by dy. Okay, so my expression here will be basically d theta by d eta t at eta t equal to 0 will be nothing but 3 by 2. So this will be 3 by 2 into k, and what is d eta t by dy? 1 by delta t, and since my zeta is equal to delta t by delta, I can write my delta t as zeta into delta. Okay, so finally, since we have found the expression for zeta, it's wiser to put everything in terms of zeta, right? So and therefore my Nusselt number can be defined as h into x by k, or in the case of cylinder, my characteristic length will be the diameter or the radius. So I will choose the diameter as my characteristic length. So this will be h into d naught. This is the diameter of the cylinder. Okay, so this will be nothing but so 3 by 2 into d naught divided by zeta into delta. So I can substitute my expression for zeta into this, okay, and I can directly simplify to get my Nusselt number expression. So my expression for h would turn out to be 0.645 into k by r into PR 1 by 3rd RE power half. Okay, So this is already in terms of PR, and my delta, I know the expression for delta, okay, so which is nothing but square root of nu lambda r by 2 v infinity, correct. So I am substituting everything into this, and finally I can write in terms of Prandtl number and Reynolds number, where my Reynolds number here is defined as v infinity into d naught by nu. So d naught is 2 times r, okay. So then you can finally get the expression for Nusselt number, which is h d naught by k, so which comes out to be 1.291 into Prandtl number power 1/3 Re power half, okay. So this is my expression for Nusselt number in the stagnation region, okay, in terms of Reynolds number, which is defined this way, and the Prandtl number. Now compare this with the similarity solution. For the similarity solution, you derived the expression for Nusselt number, that was in terms of the radius, okay. If you remember, that was NUR was 0.81 times RE based on the radius, PR 0.4. Please go back and recollect, from the Falkner-Skan solution we have determined the expression from the similarity solution for the cylinder case. This was defined based on the radius. So if you convert this in terms of diameter, okay, that is, it's a straightforward conversion. So this can be written as 0.81 v infinity into d naught by 2 times nu power half Prandtl number to the power 0.4, and you can define your Nusselt number based on diameter as h d naught by k, which is nothing but twice of nu r, okay. So if you put this, so if you multiply by 2 times, so this will be nothing but your nu d naught, and on this side you will have a factor of 2 into 0.81 divided by square root of 2, okay. So this will give you my nu d naught as 1.145 Prandtl number 0.4 Re based on your diameter power half. So this is your exact solution, right, from the similarity, from the Falkner-Skan similarity solution. So you can compare that with the approximate expression. So this is 1.29, it's almost 1.3, this is 1.14, it's very close, and the dependence on Reynolds number is the same. The Prandtl number dependence is slightly different. This is giving 0.33, whereas that is to the power 0.4, okay. So from the similarity solution you can see the agreement is pretty close, not that exactly the same, but very close to the similarity solution. So with that we will stop here today. So tomorrow let us make another assumption so that we can simplify the Karman-Pohlhausen solution itself, okay, and with that we will get the same expression for Nusselt number, and we will see how close it is. So any questions? Okay, so these approximate solutions are therefore very useful. You don't have to solve the ODE numerically, okay. So only guess some profile and substitute, and finally you find the resulting expressions, correlations for Nusselt number, especially the integral quantities like Nusselt number are pretty much similar to the similarity solution, okay, although the profiles themselves may be different. For example, if you assume a linear temperature profile, it is completely off from the actual temperature profile, okay, but the integral quantities like skin friction coefficient and the Nusselt number, you get a reasonably good agreement with the approximate solution, okay.